So as you can probably imagine, the rate of a reaction for any given reactant or product, like the rate of the reaction with respect to B or with respect to A, depends on the stoichiometry of the reactant or product. So we're going to say reaction rates are related to stoichiometry. And so, for example, let's consider a reaction that has an overall equation that would be something of this format. 2 of A, whatever A is, turns into B. So for example, maybe 2 chlorine atoms turning into Cl2 gas, or 2 hydrogen atoms turning into H2 gas. So something of that format. Because of the stoichiometry of this reaction, because we have this stoichiometric coefficient, the reactant, A, or chlorine or hydrogen, the reactant is being consumed twice as fast as B, the product, is being made. So we're going to say reactant A is consumed or used 2 times faster than our product B is made. And again, this is just stoichiometry. We have to use 2 A molecules in order to make 1 B molecule. So we're going to be using up 2 A's for every B that we produced. So we're going to go through the A molecule twice as fast as we're able to make the B molecule. Now, this becomes a little bit of a problem when we're trying to write an average rate equation in this form right here. So rate is the change in concentration of B over time. Rate is the negative concentration of A over time, where we want rate to be the same no matter how we calculate it. And that's why we put that negative sign in there, so that rate would be the same no matter how it's calculated. Well, if A is being used up twice as fast as B, the rate of A will be twice as big as B. And again, we don't want our rates to be different. We want our rate to be the same no matter how we're measuring it. So in order to deal with something like this reaction right here, we are going to include the stoichiometric coefficients into our average rate equation. So let's just start by writing the rate in terms of B, because that's the easiest one. Our product, the rate of this reaction, is equal to the change in concentration of B over the change in time. And we said that for our reactant, if we were going to do this in terms of our reactant, it would need to be negative change in concentration of A over the change in time, because A is being consumed rather than being produced. So we're going to get a negative number, and we'll put a negative sign in the equation to get rid of our negative number. Now, if we want to factor in stoichiometry, acknowledging that A is being used twice as fast as B is being made, we're just going to put stoichiometric coefficient on the denominator of this equation. Divide the rate of A by 2, and now it's going to be equal to B. And what we just did there is something that we can generalize for all reactions, no matter what their stoichiometric coefficient might be. So we're going to write a generic equation, A plus B goes to D, and E. And we can write an average rate calculation for any one of the 4 things in this equation. So for our products, it's just going to simply be the change in concentration of our product over the change in time. And we're also going to include the stoichiometric coefficient in there as well. And that's going to be equal to our other product, the change in concentration of E over the stoichiometric coefficient and the change in time. And for our reactants, we want to bring in that negative sign. So negative change in concentration of reactant A over stoichiometric coefficient and the change in time. And our last product or reactant, change in concentration of B, negative because it's the reactant, divided by the change in time and also divided by the stoichiometric coefficient. And a lot of resources are going to separate out that stoichiometric coefficient as if it's its own fraction. So you might see it written like this, but I'm just jamming all of mine together. So with this useful equation right here, let's go take a look at an Alex problem. We're working now on this problem, calculating the reaction rate of one reactant from that of another. And so here's a problem with a whole lot of words in it. It's describing a chemical reaction. It's giving us the rate of something in the reaction, and it's asking us to use that information to calculate the rate of something else. So let me take a screenshot and let's work on this problem together. So first of all, I think we need to figure out what to ignore in this because there's a lot of information in here. What are we trying to focus on? At the end of the day, this problem is asking us to calculate the rate at which nitrogen monoxide is being produced. Okay, so we understand that's our goal. And we are calculating that rate from 570 liters per second of dioxygen are consumed. So we have the rate of our dioxygen, and we're trying to use that to calculate the rate of nitrogen monoxide. And so that means that we're just going to do, a rate of change in concentration of something per time, and that's going to be equal to the change in concentration of something else per time. In order to do a problem like this, we need to know what the stoichiometric coefficients are, which means that we need to start by balancing an equation. And the reason that there are so many words in this problem is because they want you to write the equation from all the different words. So we're going to find where it tells us what the problem is. In this reaction, gaseous ammonia. If you're not sure what ammonia is, just Google it. Just look up its formula. It's NH3. Gaseous ammonia reacts with dioxygen, so that's O2, to produce nitrogen monoxide, that's NO, and water. So now we need to balance this equation. And I think to balance this equation, the first thing that I'm looking at are 3 hydrogens on the left, 2 hydrogens on the right. So I'm going to bring both of those up to 6 hydrogens. Now I have 2 nitrogens on the left, and now I also have 2 nitrogens on the right. And in terms of oxygen, I have 1, 2, 3, 4, 5 oxygen on the left. So that means that I want to double everything. Now I have 1, 2, 3, 4, 10 oxygen on the left, so that means I need 5 O2. So now I have my equation balanced. And then let's highlight the information that we have in the problem. We have information about O2, and we're being asked to calculate the rate of the reaction of NO. So what is the relationship between these two guys? Well, O2, change in O2 per time. O2 is a reactant, so it's a negative delta O2. And the stoichiometric coefficient on O2 is a 5, so we're going to put a 5 down here. And then our NO, it's a product, so that's a positive change in concentration over time. And the stoichiometric coefficient for that guy is a 4, so we got to put a 4 down here. So what do we know? We know that the rate of the oxygen is 570 liters per second. So that means that the rate of the oxygen, just the oxygen, is 570 liters per second. Now you might be wondering, wait a minute, what happened to the 5? Why is the 5 all of a sudden gone? The 5 is not included, the stoichiometric coefficient is not included in this particular calculation because in this particular calculation, we are just looking at the rate of oxygen all by itself. It's not asking about the rate of the reaction. It's not trying to compare one thing to another. So these forms that we have up here, these forms are going to give us the rate of the reaction, a number that is generic and standardized for all of the substances in the chemical reaction. The data that we have and the information that we have for dioxygen is specific just to dioxygen all by itself. So what we're going to do is take this term, which is equal to 570 liters per second, and we're going to plug that into this part of the equation. And so we are going to get 570 liters per second over 5. I'm going to slow this down a little bit for you because I know this is tricky. So we're taking delta O2 over delta T, that's this stuff right here, and we are substituting 570 for that number right there. But nothing has happened to the 5. The 5 is still there. 5 needs to be there to make this a rate of reaction instead of making it just a rate of oxygen. That is going to be equal to delta NO over 4 delta T. What are we trying to figure out? We're trying to figure out the rate of nitrogen monoxide. So the rate of nitrogen monoxide is this portion right here. Just like over here on this equation, the rate of O2, maybe it'd be helpful if I wrote that. The rate of the O2, the rate of O2 is just delta O2 over delta T. The rate of NO is just delta NO over delta T. So what we need to do is solve back over to here. We need to solve for this part of the equation. And what we need to do is take this 4. We're going to multiply both sides by 4 to get the 4 out of the right side of the equation. When we solve, we are going to end up with the rate of the NO. 4 times 570 divided by 5 is 456 liters per second. 456 liters per second. Now we have another problem because Alex wants us to give it the answer in kilograms per second. So things are going to get even trickier, and I need to make myself some room here. We need to do a conversion from liters to kilograms. There's a lot of stuff going on in this problem. So we have 456 liters of nitrogen monoxide per second. How can we relate liters to kilograms? Well, if we had density, that would be ideal. We don't have density, but we are dealing with a gas, so we can use the ideal gas law, PV equals nRT, because we know the pressure, it is 0.62 atmospheres. To save space, I'm going to leave the units off. We know the volume is 456 liters. We know R, the gas constant, 0.08206 liters atmospheres per mole Kelvin. And we know our temperature is 246. Convert that to Kelvin. It is 519. So this is going to tell us how many moles we have. 0.6 times 456 divided by 0.08206 and 519. We have 6.64 moles of NO. We can do a mole to gram conversion for NO. We have 30 grams per mole, 14 plus 16, and we have 1,000 grams in a kilogram, 6.64 times 30 divided by 1,000 gives us 0.20 kilograms per second. Let's see how we did. Let's practice that some more.